In this video, I'll be working through some sample problems applying the work energy theorem to find speed when given work and energy and to find the distance. These sample problems come from the OpenStax AP College Physics textbook. In this scenario, a package has 3.75 joules of kinetic energy and 92 joules of net work is done to push the 30 kilogram package against 5 newtons of friction. We're asked to find the speed of the package at the end of the push. So we'll draw a diagram. We have our 30 kilogram package. There is a push force and there is a frictional force. We'll go ahead and list our knowns. The initial kinetic energy of the package is 3.75 joules. The net work is 92 joules. Mass of the package is 30 kilograms. And the frictional force is 5 newtons. Okay, so I'll write out our formula for net force. And if we have a look at our givens, we are given the value for the net force and we're given the initial kinetic energy. So we can substitute these two values in to find the value of our final kinetic energy, and then we can use that to solve for our final speed. So that will be equal to the net work done, 92 newtons, plus the initial kinetic energy, 3.75 joules. Did I say newtons? I meant joules. Which will be 95.75 joules. And now we can rearrange that to isolate our final speed. So to get rid of this half, we can multiply by 2. We divide by mass, and we find the square root. So we can substitute our known values in there. 95.75 multiplied by 2 divided by the mass, which is 30 kilos, and then we find the square root of that value, and that will give us 2.53 meters per second. And a carry on to the same scenario, we're asked how far does the package coast after the push, assuming that friction remains constant. So for this one, we actually want to go back to, rather than using the work energy theorem, we want to use this formula here, so that we can find distance. Now, the friction force is the only force that applies to the scenario because the pushing is finished, so there's no push force anymore. So the frictional force is the only one we're interested in, which means that this is our frictional force. And therefore the work being done, the only work being done is also work by friction. The package is travelling in this direction, but the frictional force is parallel but in the opposite direction. meaning we do not need this part of our equation, but our value is going to be negative for work done by friction. We saw in the question above that our frictional force was equal to 5 newtons. We weren't given a value for work done by friction, but we can figure that out. So our package is travelling an unknown distance and it'll stop. And when it stops, it'll have a kinetic energy of 0. It won't be moving anymore. The kinetic energy that we worked out up in the above problem at the start or after the push, so this is our final kinetic energy, and for this part of the scenario here, our initial kinetic energy is equal to 95.75 joules, which means that the work done by friction needs to remove this amount of kinetic energy from the package. And as I said, it will have a negative value because it's in the opposite direction. So we can substitute our two known values here and rearrange the formula to find distance. So distance will be equal to work done by friction over the frictional force, which is negative 95.75 over 5.00, which is 19.2 meters.